like a alley of commerce.
Yeah.
But then they took that stuff down because I wasn't.
That makes no sense for the modern world.
Because London was very particular about their bridges for a long time. Like they didn't want other bridges for the longest. They're still pretty. I don't know why I watched a bridge documentary, but
that's okay. We have all done that.
Yeah, we've all watched.
In fact, that is a prerequisite of this class. You have to have watch something without knowing why.
Yes, that's fair. That's true.
All right.
Like,
so the first thing I'm going to do is to take a look at this algorithm written in Prolog, because I think it's like a perfect meld between two topics. One would be the graph searching algorithms, finding the shortest path, and then the other one would be predicate calculus, which to us is mostly just Prolog programming. So this is an interesting combination between the two. So what I would do is I am going to show you the last predicate first, and then we'll go ahead and test it. So the last predicate is shortest path, and this is not called. All right, so xy is will be the vertices, from which vertex to which other vertex. And then n is interesting because n basically gives us an idea of how to set up a boundary. And there are two ways to read this program. One way is to read it from the last predicate, and then the other one is to read it from the most elemental predicate. I suppose we can do this, kind of bottom up approach. So we can look at boundary first. So boundary is there are two predicates related to boundary. One is a base case, which is the end of the recursion. Then the other one is recursive, because in order to prove this particular boundary, you need to prove this boundary first. So let's check out what is boundary, the non-recursive one. So with the non-recursive one, we have x, which means it is the same vertex, and then n is 0, and becomes 0, and h has to be greater than or equal to 0. So that is, that sets up, the non-recursive version of boundary. And then the other one is recursive, which basically says h has to be greater than 1 instead of greater than or equal to 0. And then we have to find an edge, okay? So the two vertices is x and y, and then we have to find a vertex z such that there is an edge from x to z with a cost of n1. The third item here with each edge defines the distance between the two vertices. So this is n1, and then h1 is h minus 1. So whatever this h is, we subtract 1 from it. So h is basically the number of hops. If you go over one edge, it is counted as one hop. So if you have a path that consists of 5 edges, the two vertices connected by those 5 edges would be called 5 hops away from each other. So h1 is just 1 less than h itself. And then the boundary recursive call is going from z to h. And this time we have n2 as another cost. And then we have h1 here, which is 1 less than the other one. So the recursive version of boundary is trying to find a path between x and y, using h as a number, as a counter, to basically count how many hops do we have left. And then n is the sum between n1 and n2. So n is basically the distance in order to go from x to y through all the edges. So are we reading this okay or not in terms of finding out what boundary does? Questions of any kind? So this is one of the things about Prolog is it doesn't have a whole lot of types. You don't have to declare your variables, and it is read just like kind of if then else statements. And remember, this is the part that is the condition. This is the left-hand side of an implication, and this is the right-hand side of the implication, even though it is the left and the right are reversed when we look at these. Yep.
What is the h variable?
H is the number of hops.
Oh.
Number of hops. In other words, how many edges are we allowed to use to go from X to Y.
And then N is like the distance.
N
between
is
two
the
edges.
distance, right?
Yeah.
Yep.
Why do you initialize every like boundary twice?
You mean these two?
Yeah.
Because this one only has XX in it. In other words, this one says, we are getting to the point where we are looking for a path from a vertex to itself. So since you don't need an edge, so that means in that case, as long as h is greater than or equal to 0, we'll be fine. Okay, so it meets that requirement. And then n is 0 because the distance from a vertex to itself is going to be 0. You don't need to traverse an edge to go from a vertex back to itself.
So it's a base case.
Huh?
It's kind of like a base case.
It is a base case.
Okay.
So with Prolog, you always define the base case first because the way it works is it will try to match from in the order that your predicates are defined. So it always goes for the first one, line 10 first. If line 10 does not match, then it will go for line 11, which is a recursive call back to the first one. All right. So we can check this out, right? So we can check out. This is how a graph is defined with all the distances kind of built into the edges. The first line says we can go from V0 to V5, and the distance of the edge is 3, and so on. So now we can go ahead and let's see. I'm just looking for what the graph is going to look like and which one is good as the first where we're going from, and which one is good for the destination where we're going to. So V0 goes to V5, V5 goes to V4, and V4 is the terminal. And then V0 goes to V1, V1 also go to V4. So I think, generally speaking, we want to go from V0 to V4. So let's go ahead and do that. So we say boundary, V0 to V4, and then we can say, we can make the distance or the length of the shortest path basically a variable. So we can say L in this case. And then we can give it the number of hops. So if you don't give it enough hops, and it cannot get to V4 from V0, it will just return false. So it just says, nope, we cannot find a way to go from V0 to V4, given that I can only traverse one edge. Is that okay? So now we can say, oh, okay, that's not enough. Let's increase it by 1. So we can increase the number of hops or number of edges that we are allowed to use to 2. And then we compute again, and it still cannot find it. And this is doesn't look right to me because V0 to V5 and then V5 to V4. So these two should work. All right. That doesn't work out. All right, so let me check again. H is greater than 1. It is. And we can find an edge of V5. That's going to be our Z. N1 is going to be 3. H1 is going to be 1. And then we try again. And then this time, okay, I see why it's not working. Because H1 becomes 1, and then we do the recursive call, and because H1 is 1, 1 is not greater than 1, so it failed. So we have to increase this to 3 at least. Then you can find a path where the length is 6. Is that okay? All right. You can always click next, so you can find alternative path. The other path is only 5 because we can go from V0 to V1, and then that's a distance of 3. From V1 to V4, that's also a distance of only 2. So that's why we found the length of another path using 3 hops to have a path of only a distance length of 5. And then we have a length of 3, The length of 3 is right here. V0 to V3 has a distance of 2. V3 to V4 has a distance of 1. So 2 plus 1 is a 3. And I think that's the shortest we can find. And that's it. All right. So do we have any questions about this little demonstration? It found all the paths. It found the length of all the paths that has 3 hops or less. And you don't have to do anything on your side, when you're coding it, to say, okay, but I don't just want one path. I want all the paths. And this has to do with Prolog being able to do what we call backtracking. Once it finds the solution, it knows that it can backtrack and look for another alternative that also make the predicates true. Is that okay so far? In fact, this is one of the biggest differences. The biggest difference between Prolog and Lisp. LISP is Lisp, which stands for list processing. It is also a functional programming language. It inspires a lot of current modern programming languages. Lisp, not so much Prolog, but Lisp does not have built-in backtracking, which means if you want to explore all the alternative options, you kind of have to code. You have to make sure that it will consider all the options, whereas your predicate calculus or Prolog would automatically explore all the possibilities. Because it's not looking at things from a procedural perspective, it is looking at things from a predicate perspective. These are all basically predicates. These are all conditional statements. The first one can be read as, if h is greater than or equal to 0 and n is 0, then boundary x and h is true. Okay. The second one, kind of more complicated as the left-hand side, but nonetheless, it is just an if-then statement. And it is up to the engine, up to the language implementation, to basically look at all the possible ways to make a predicate true. So that saves you a lot of trouble if you're looking into alternatives. So in the case of finding the shortest path, well, I mean, this is kind of handy, except we have to cast the problem of finding the shortest path into the format of predicate calculus. And that's going to be that's a little bit tricky, because now how do we ask the Prolog engine to say, okay, I want you to find me the shortest path. I'm not going to tell you ahead of time how many hops we need. I'm not going to tell you ahead of time, what is the boundary. In other words, n, which is the length of the path, I can use it as a constraint. So let me show you what I mean by that. I can change the query and say, this is now a constraint. So in addition to making 3 hops a constraint, I'm also making the length of the shortest path no more than 5. So now we have 2 constraints, and I'm asking, can we find a path like that? The answer, there should be 2 answers to this. Okay, so Control Enter. That's true, and that's false. So you can only find 1 path. I think that's because 5 has to be, this has to be exact. So you can only find 1 path where 5 is the exact answer. Is that okay? Are we good? Okay. So now we're trying to look at the next one, which is find boundary. So find boundary is making use of boundary. And it's also, there are 2 of these. One is, quote unquote, non-recursive. It is non-recursive from the perspective of find boundary. Because find boundary, the first one, starting on line 18, is only using boundary as a predicate. But the one on line 21 is using find boundary itself, also a part of the predicate. So let's check out the first one. The first one is super easy. If the engine is asked to find boundary x, y, and h, it just passes it along to boundary, and that's it. Okay, so nothing too fancy about the first one. It looks like just an alias of boundary. The second one is a little bit interesting because it is given, x, y, and h, and we're supposed to find the boundary. But instead of just using boundary, the first thing it does is to say h1 is h plus 1. So whatever this h is, I'm going to add 1 to it. Okay, I allow myself one more hop. And then it's going to call your find boundary again, but this time with h1 in it. Okay, so what is it doing? So this will only get to line 21 if line 18 fails. Because it would, if you say, okay, let me change the query to make use of find boundary. Okay, and we'll give it some unknown here, okay, because we want to find the length, and this time I'm going to be unreasonable and say the constraint is 0. Okay, this doesn't sound very reasonable because we are saying you go find the boundary of going from v1 to v4. I want you to tell me what the length is, but you are only allowed 0 hops. You go like, that doesn't make sense, okay? Well, it doesn't make sense because it will automatically fail line 18, because line 18 is just saying, okay, I don't know how to get this job done. I'm going to call boundary. Boundary says, as long as h is greater than or equal to 0 and n is 0, but you need to be on the same vertex itself. If I'm specifying v0 and v4, they are not the same. So it would fail the first boundary. The second boundary is bound to fail as well because h is only 0. 0 is greater than 1 is false. So it's going to fail both of the boundary. So this boundary is going to fail, which means this find boundary is also going to fail. But if the first definition of find boundary has failed, it will automatically move on to the second one. So now we say, okay, with the second one, the first thing I do is I allow myself one more hop. So this is the looping mechanism of Prolog. Okay, what we normally see as for h equals to 0 to whatever high number you want to set up as the boundary. With Prolog, we don't set up a loop. A loop is very implicit. It is done by recursion. So now we increase the number of hops to 1, and then we try again. If this fails, if line 18 fails again, when the number of hops is 1, it goes back to it will go back to this one, and then this time we say, well, let's bump it up one more time. So now it will keep going up until we find the right number of hops to find a path from v0 to v4. Is that okay? Well, let's see whether this works or not. Oops. Control Enter. So it finds L equals to 6, 5, 3, and it will keep going like this. It's not going to stop because it's finding the number of hops, it keeps increasing. That's the problem. It doesn't know when to stop. Okay, so it will say, okay, we found paths already, but it will continue to go like, if I increase the number of hops by 1, I will find new paths because there is a loop in here. You can see how v0 goes to v2, v2 goes back to v0. So it can basically go into that loop and then get out of the loop to go back to v4 through one of the paths. And that's why this is not going to end. It will keep looping around, and it will keep finding paths that are more than what it used to be, and it's not going to stop. Just because it keeps looping, because of a v0 to v2, v2 goes back to v0 because of that loop. Okay, so that's kind of useful because I don't need to predefine the number of hops, but it's not useful in the sense that it doesn't know when to stop. Because I want this to stop as soon as I find the shortest path. So that's why we have find boundary, but it's not the one that we are going to use. So now we have path bound as a predicate. So path bound as a predicate, there are also 2 of these. One is non-recursive, starting on line 25. The other one is on line 30, which is recursive. So the first one is path-bound non-recursive. So it is going from x to y. We want to find the length of the path, which is n, and then L is a, how should I put it? It's a lower bound. So L is a lower bound, which means as long as the actual distance of the edge is less than the lower bound, then we declare, yep, this works. Okay, let me say that one more time. So path bound is asking, do we have a path going from x to y using L as the lower bound of the length of the shortest of the path, and then n is the length of the shortest path. So n is the actual length of the path between the two vertices, and then L is a lower bound. So I can basically say, don't go further than this. And why is that useful? Because once I do this and combine that with find boundary, then I can basically tell find boundary not to exceed a certain point. Because once it exceeds a certain point, we go like, okay, this is useless because we found a path of a shorter length already. There's no need to go loop around this loop a few times and then go again. Not sure whether this is making sense or not. Maybe a little bit. Okay, so maybe after I finish explaining everything, including shortest path, it will make more sense to you. So path bound in the recursive way means this will only happen, we only look at line 30 after line 25 has failed. So line 30 is asking the same question. I'm asked to find a path from x to y using L as a lower bound, and n is basically what we want to use to return the actual length of the path. So this time L is greater than or equal to 0. It is a requirement that the lower bound, I still have enough lower bound left to do something. We find an edge from x to z, not from x to y, just from x to z. And this edge has a distance of n1. And then L1 is L minus N1. So L1 is the new lower bound because I'm given a certain allowance, so to speak. I spent that allowance on the first edge where it has a length of N1, a distance of N1. So the left behind allowance is L minus N1. This is how much I have left behind to solve a subproblem. The subproblem is to go from Z to Y using N2 as a length of the actual path, but this time the lower bound is L1 because I spent N1 already, and L1 is my own allowance minus N1. Is that making any sense at all? Maybe? Sort of. Any questions? Okay. So if path bound is returning true, that means I did find a path from z to y using L1 as it's actually the upper bound because we cannot find a path longer than that. But the actual length of that path is N2. So now I can now come up with my own answer, which is to go from x to y. I use this edge to go from x to z with N1 as its distance. Then I find another path from z to y with N2 as the actual length of the path, N1 as the upper bound. So my own answer is N, which is N1 plus N2. That's the length of the path from x to y. Is that okay so far? Well, let's find out whether it works or not, okay? Because path bound is allowing me to specify a upper bound, which is L, and we can find the path length N from x to y. So what we can do now is I can change my query to path bound, go from v0 to v4, and n is a variable because I want to find the length of the shortest path. At this time, I can give it an L that is an upper bound. So we can give it 7 as an upper bound. and it will find a path with a length of 6, a length of 5, a length of 3, a length of 5 again. This 5 is actually the 3 plus 2 because of one loop around, and that's it. In other words, the upper bound helps me to stop, find boundary. Well, this is a mechanism so we don't go forever looping around. Is that okay? All right. So now we look at shortest path. So shortest path is the actual code that will find the length of the shortest path. So the first thing it does is find boundary, and it's using x, y, n, and then a 0. So it would basically just find the length of a path from x to y, and it doesn't have to be the shortest. It just finds a path. But it will know the length of that path already. This backslash plus here is negation. Yeah, I know it doesn't look like negation, but it's saying negation. It's saying basically not. Okay, so this is n. The comma is n. Backslash plus is not. So it's basically saying you'll find a path of length n from x to y, and not path bound xy underscore. So underscore is also a variable, but it's not even a name because I don't care what it is. It's basically saying there is no path from x to y that has a length of less than n. The exclamation point here is what we call the cut operator, but I'm not going to explain it just yet, okay? Because I want to focus on line 38 and line 39, because between these two, it is finding the length of the shortest path. The question is, how does it know something is the shortest? Because line 38, okay, we have shown already, line 38 comes up with just about all the possible ways. You can loop around something like a few times and eventually still be able to get from where we need to go to where we need to go to, and we'll still count it, and that's why it gives you it doesn't, if you have a loop in your graph, it will give you it will give you an infinite number of solutions. That's what find path is going to do. The magic is path bound, because path bound is basically saying, find me a path from x to y with n as a length. But also make sure that there are no path that has a shorter length. That's what the not path bound xy underscore n is trying to say. So I'm stating the objective of what we need to do. Give me a path, and there's no shorter path than that. Well, if I'm saying, give me a path P, and there's no shorter path, doesn't that just say that path P is the shortest path? So I am stating the property of the shortest path, but I'm not stating the actual quote-unquote algorithm of doing it. Is that making any sense at all? Well, let's check out whether it works or not, okay? So we'll go ahead and use shortest path. So shortest path, go from V0 to V4, and tell me what is the length of the shortest path. It just finds 3. So are there any questions about this particular program? Because it's kind of a weird combination between Dijkstra's algorithm, which is definitely a conventional algorithm with a while loop, with a conditional statement, and then for each loop inside the conditional statement. Nope, the other way around, with a for each and then a conditional statement inside the for each. But it is a very traditional way to express an algorithm. This one is kind of doing the same thing, except it is by stating the nature of the problem, and it will solve it for you. So are there any questions about this particular program or the approach of using Prolog? see. I can see some squinting. I'm watching the TV series Bones, and in that particular series, the FBI referred to the civilian experts as squinters. How many of you have watched Bones as a TV series? Do you remember Squinter?
Yeah.
Yep. So I'm trying to look for squinters in this class. It's like,
Yeah. That's from yes, I understand.
so how would you like to write programs using Prolog? So forget about C, C++, Java, or JavaScript. We'll just use Prolog. It's just a different way of thinking. All right, so what is the cut operator doing here? What is the exclamation point? What is a cut operator? A cut operator means if we ever get to this point, do not backtrack. Don't look for any alternatives. We are done. That's what the exclamation point is trying to say. So basically, it will bounce between these two. It will find a path where n is 6, okay? And then it's going to move on to path bound, and we'll find that, oh, guess what? We found a path with a length of 3. So path bound is going to return true, but this is a negation, remember? So if path bound is true, not path bound is going to be false. So the Prolog engine goes like, let's backtrack to the first one. Give me another solution, okay? So the next solution is, oh, okay, I found another path with a length of 5, okay? And then move on to the second one. It will say, okay, let's try to find a path bounded by 5 as the upper bound, as the upper limit. But do we find another path with, that has a length of less than 5? This thing comes back and go like, yep, there's a path. The negation says, okay, so if path bound is returning true, then not path bound is going to be false. Prolog goes face palming again and go like, okay, let's go back to find boundary again. So it's backtracking automatically to try to find the next available solution. This time it found the path with a length of 3. So n becomes 3. So then it goes back to path bound again, and they ask, well, can you find me a path that is that has a length of less than 3? This time path bound goes like, nope, can't find anything like that. The answer is false. Not false is true. So now we have true and not false, which is true. So we get to the cut operator. So by the time we get to the cut operator, we have already confirmed that we have found the shortest path, because we could not find a path that is shorter than the path that we have found on line 38. So this whole thing works because of the internal built-in backtracking capability of finding alternative solutions. Are we okay so far? Now, the ability to find alternative solution was already demonstrated when we used the ancestry example, because we were able to ask who are the offsprings of Homer, and it was able to find both Lisa and Bart. So for the same reason in here, it will also be able to go back. If the second statement or if line 39 is returning a false after the negation, then it's going to go back to line 38 and say, hey, give me another solution. And we'll keep asking line 38 to find a solution until line 39 says, okay, there are no shortest path, there are no path with a length that is shorter than n. Then it will go to the cut operator, which basically means, okay, just exit. Okay, we're all done here. No need to go back to find alternatives because we have found the shortest path. Are we doing okay so far with this? Maybe? Not seeing any questions, but I'm pretty sure that not everybody knew exactly how this program is getting the job done. It's just, that's basically Prolog. Are we okay so far? All right, so changing the subject just a little bit, still staying with graphs. I did look up Dijkstra's algorithm, and in 1953, I think, that when the algorithm was published, it was considered artificial intelligence. And so there are two big camps of AI or artificial intelligence. There's strong AI and there's also weak AI. How many people know the differences between what is considered strong AI and what is considered weak AI?
You explained this a few class sessions ago.
I did. Okay, very good. So you remembered.
I think so. You said strong AI uses neural networks.
It's more like strong AI attempts to recreate how we think. So we are trying to make computers think the way we do. So it will be capable of doing things that we can do. Weak AI, on the other hand, is using algorithms to solve very specific problems. So Dijkstra's algorithm is a prime example of weak AI, which is basically a completely algorithmic approach of saying, okay, this is step by step, okay, very rigidly how we solve this problem. That's weak AI. So right now the focus is mostly on strong AI because neural net is kind of like internet back in year 2000. I know some of you were not even born in 2000, but so I can remind you what happened in 2000. Okay, so in 1998, or 1999 or so, the internet basically, in terms of the hardware and the availability and affordability, it just got past a certain threshold. So a lot of people gained access to the internet, and also the internet speed becomes realistic. Okay, that people can transmit content, multimedia content, and so on and so forth. So it presented a huge opportunity for people to do things over the internet. For instance, selling stuff online. Okay, Jeff Bezos, basically, started up as a book company. That's what Amazon used to sell, was just books. So that's
diapers.com.
Huh?
And then they bought diapers.com.
They did?
Yeah.
I did not know that.
Yeah. Amazon bought diapers.com, and it was like a famous loss because the .com bubble.
Yeah. Mm-hmm.
Yeah,
it became the .com bust. Basically, the boom became a bust. But basically, because of the availability of technology, the infrastructure being installed, and the price point of getting internet access became affordable to just about most families. So they got a .com boom at the time because people thought of all the cool things they can do with the internet. We are seeing basically the same thing with neural nets. Because Google made this chip to perform all the calculations for neural nets in hardware. So it's very much hardware assisted to save them a lot of power. Remember, how much data processing power you can fit within a building is limited by how much heat you can extract. So if you can find a very energy efficient way to do something, that's a really good thing. And that's what Google did. Okay, Google basically invented their own chip to perform all those high level neural net calculations, so they can pack a lot more calculations within the same enclosed space compared to before. So basically, what we're looking at was and still is an increase of the ability to utilize neural nets. And as a result, people say, oh, okay, can we solve this problem using neural net? Can we solve that problem using neural nets? And that's basically what we're looking at this point is we're trying to cast a lot of problems into neural net problems and try to apply neural net to solve those particular problems. So it is not unlike the dot-com boom, about year 2000, where a lot of startup companies, a lot of people, were kind of getting into this whole thing and looking at the possibilities. And every time there's an opportunity like this, where's the money coming from? I mean, you cannot just make a company out of thin air. You need money, right? So where's the money coming from? what is driving all the industries in San Francisco, San Jose, the whole Silicon Valley, and a few other places? Where's that money coming in from? Investors, very good. That's a good answer. What type of investor? Would it be Warren Buffett?
No, it's like venture capitalists, isn't it? Isn't it venture capitalists?
Venture capitalists, very good. So venture capitalists were providing the fuel, back in around 2000, when the internet was just, getting over that point to become like, oh, there are a lot of possibilities. So what is the difference between a venture capitalist versus a normal investor like Warren Buffett?
So Warren Buffett invests in companies that are already set, where venture capitalists bank off potential and like owning a portion of the company. And if it gets big, they can sell off that big portion. So they go in low, and well, they do the Warren Buffett thing, buy low, sell high. But if you're getting in on the ground floor, then you're going to make a lot more money than getting in after the fact.
So one is time frame, right? Yeah. So Warren Buffett is not looking to make a lot of money over 6 months or a year. I mean, he doesn't want to lose a lot of money, but he's more patient. His investing strategy is more long term. So he's looking for, well, I know it can rise and it can dip, but we can ride this out and looking at the longer trajectory. Mm-hmm. The venture capitalists are not doing the same thing. They are very short term because they basically approach people who are wealthy, like dentists. And trust me, nobody would think about dentists as like the fuel behind all the venture capitalists, but they are, because dentists actually make a lot of money. Yeah. In fact, they also have a very high suicide rate. Yeah. Think of that. I mean, isn't that kind of mind-boggling that the people who make a lot of money actually has a high suicide rate? Just think about their job.
As a boredom.
I mean, what do you see every day? Right? And every single time there's a problem, and when you have teeth problem, it smells. So that's their job day in and day out. They make lots of money, but yet, with all that money, they don't know what to do. So, so they have, these venture capitalists to help them, quote unquote, invest the money. So how do you convince a dentist to give you money and go like, hey, give me some money, I can make you really rich. And in the process, I'm making myself really rich too. Thank you very much for your investment. So how do you invest? How do you convince people to give you a lot of money for investment?
They'll get rich too. They can retire.
But you're guaranteeing a high return. Okay. So what you're trying to do is to guarantee a high return. So you're not looking at the stock market. There are certain types of stock where they give you a lot of that term just escaped me right now. Dividends, exactly. So they're dividend-based investment where your big chunk of money will give you like X%, pretty low, usually 5%, 3%, 4% of return, but it's pretty reliable. So year after year after year, you get like 3-4% of return. That's not what venture capitalists would say. It's like, we'll double your money over a year. All right. So now you're taking all of this money from these kind of wealthy individuals. You pour all that money, and then you're looking at a new technology like the internet back in year 2000, and the neural net. The internet back in year 2000, and the neural net today. Yep.
So what you're saying is when the neural network bust happens, there's going to be a lot of dentists that kill themselves.
They won't. I mean, they kill themselves not because of the investment tanking. It's just some weird psychological thing that's causing, the dentistry or dentists, within the dentists, they have the highest suicide rate amongst the professionals. We can kind of understand that lawyers won't do that. Yep.
I was in high school, and doctors have high suicide rate too, because that kind of appeal to like the insurance companies. So they're always kind of worried about like someone suing them. So that's like fun too. Also, they have law firms, so like ships.
Well, that's the same thing for dentists too, because dentists are doctors.
Mm-hmm.
It's a doctorate to be a dentist.
Yep.
sure.
Yeah, I feel kind of bad for you. You spend like 10 years of your life, and then
Yeah.
They're like 30 and they have like $500,000 in debt or something like that.
Yeah.
That's why.
But they also make a lot of money.
Yeah, they do.
Well, at
Yeah.
UC Davis, I know that they like allow you to get like what's it called? You know how people can get like healthcare and stuff like that through their jobs. You can also get like legal insurance too, so that when you get sued
Yep.
as a healthcare professor, that professional.
That's only applicable if you're a private practice, so you can work for a company, because there are, organizations. If you're an employee, they're gonna sue your employer, so you don't get as paid as much because you're not pocketing 100% of the profit, but at the same time, you also don't have to worry too much about being sued because it's gonna be your employer, which probably has a really good, insurance policy in place. So. But the bottom line is, so you have all of these venture capitalists investing in all of these companies, and they're not investing in Google or Facebook or Pixar, all of these really kind of big established companies. They're investing in smaller companies, people who say, I got a great idea, okay, because these people are the ones who can take something small, make it bigger, and then sell it to the bigger company. Like they can sell it to Google. I mean, look at all the companies that Google, Microsoft, Facebook have bought over the years. So all you have to do is to get to the IPO point. Okay, the venture capitalist just has to get to the IPO point, and then once the company IPO, if you hold any stock, you get a lot of money in return, and then you're good to go, right? Um, so I think we are looking at something similar to what we saw in the late 90s, year 2000, with neural nets. And there are problems that cannot be solved using strong AI. But now we are putting all the chips into strong AI. But that's just my opinion. And who am I? And I teach at a community college, and I'm not a research scientist of any kind. But I can see the pattern. But that's just kind of me. Anyway, are there any questions about Prolog? No. Yep.
Could this be used to solve, I was thinking about it, Einstein's riddle.
Which is?
I'd have to look it up to like explain.
Okay.
So there's like 5 different people in 5 different houses.
Uh-huh.
It's like green, red, blue, white, and black house.
Okay.
Each of those people have a different nationality, and each of those people have different pets, drinking habits,
Okay.
and smoking habits.
Okay.
And given a clue of, a certain set of facts, say,
Mhm.
The British person lives in the red house, the person who lives in the blue house, smokes this sort of cigarette, can you figure out, who lives where and drinks what and, has what nationality?
It does seem like a problem that Prolog can solve.
Yeah.
If all the facts are presented and you present also the rules in the right way, I think that probably can be solved using Prolog. I mean, Prolog is just a big, huge brute force mechanical approach of doing things using logic. So as long as the logic itself is sound and you can encode the mechanism as predicate calculus, it should be solvable using Prolog. In fact, if you look up that puzzle or that problem and Prolog, I will bet you that some people have already solved it using Prolog, and there are probably examples already in existence for that. All right, kind of cool. I think it's kind of cool, okay, because what I can see, well, this is also just me being a community college professor. I think if people can somehow combine Prolog, which is an engine that's based on predicate calculus, and big data, okay, which is basically big data is there's one aspect of big data is really just a backend. How do you represent captured data? So the traditional way of capturing data is a database, okay, tables, join operations and so on. And it has limitations, okay? It has certain type of limitations, like the quantity of data that you can store within a single relational database. The problem with the relational database are the join operations, which is also its greatest strength. The problem is, if you want to join two tables, that operation it's not very scalable. You cannot just say, I'm going to double the amount of servers and I'm expecting the time to cut in half. It doesn't work that way. Okay, there's a certain sequential, choke point that we cannot overcome when it comes to relational database operations related to the join operation. So big data is going the opposite. So what it does is we are not going to store things in a very neat, compact, non-repetitive way. In fact, it's going exactly in the opposite direction. Okay, let's just replicate and duplicate everything, because this way I can actually increase the number of servers and expect a speed up that is proportional to the number of processors. So that's the big data approach. So how does that relate to Prolog? If you can represent a lot of information, such as your grade every semester with every single subject and so on and so forth, then this can be a querying mechanism. So if you combine the ability to backtrack and also to express complex logic of Prolog, and the ability to store massive amount of data using big data, I think there are certain things we can do with that kind of combination. So that's just me, and no, I'm not starting a startup company. So, these venture capitalists, can save their breath and not approach me because I'm not doing anything. That's not worth my time and energy. And I'm not kidding you. I've worked for one startup before. They finished the product. They couldn't decide what to do with the product. And then the venture capitalist look at their financial books, look at all the numbers and go like, oh, well, you guys are sitting on stuff, okay? I'm not seeing a clear plan that you guys know how to market this and so on. So they pull the funding, and there goes the venture capitalist. No, there goes the startup company. I also knew people who basically worked for startup companies until they got married at a pretty late stage in life. So they spent like 15 years or something like that, just working for startup companies, and never really made it, unfortunately. That's a lot of hard work, okay? Because working for a startup company is hard, because you have to wear multiple hats, lots of pressure, deadlines, and so on and so forth, and not to get anything out of all of this investment, that's hard. I mean, I would enjoy solving the problems, but I would certainly not enjoy solving the problems, getting the product, but only to get the funding pulled out of the startup company and then have to start all over again. So that would not be fun. All right. So if there are no questions about this, I also want to continue with time complexity. So this time, we are working with the categories of time complexity. Yes, so we are making a hard transition into something that's super math-like, from something that's a little bit loose and kind of just a general discussion. But, this is going to be interesting too. So we want to look at linear search. There are some prerequisite modules. I don't think we need to go over every single one of these. So we can just take a look at some of these quote-unquote prerequisite modules. This one talks about recursive definition and algorithms. I suppose we can take a quick look. It doesn't hurt. All right, so we can start with what is recursion. I mean, do you guys know what is recursion? Okay, can someone tell me what is recursion?
Defining a function within itself.
The definition of a function makes use of itself. Yes. Well, it doesn't have to be direct, but eventually it does, right? It can call some other function that eventually will call the function that was called in the first place. All right, so we can look at recursive algorithms. Factorial is one of the ones that we use a lot, okay? So if f of n is to find the factorial of n, we can do it recursively, which basically says if n is greater than 0, then the result is n times f of n minus 1. Otherwise, the result is just 1, and then return the result. Okay, that's classic, recursive algorithm. And then we look at Pascal's triangle. Okay, Pascal's triangle. That reminds me of something, but when did we see something like this? Does anyone remember when we looked at something similar to this? There's a particular theorem.
Binomial theorem?
The binomial theorem, not quite, okay? This leads to the binomial theorem. This one only deals with the coefficients. So it does have to do with Pascal. It's called Pascal's identity, exactly. So when we proved Pascal's identity, we saw something like this, okay? So it's recursive, okay? Is this the best way to come up with the Pascal's triangle number? No, not even close, okay? But it is a way to do it, and it is recursive. And then we have Tower of Hanoi. So the Tower of Hanoi, how many people know what is the problem? The Tower of Hanoi problem, okay?
You have to move a certain number of rings from one kind of, I don't know, what is it, pole to another.
Poles, there are 3 poles.
But you can't stack like a bigger one on a smaller one.
Exactly. So the problem is, we have 3 poles, okay? All the disks are on one particular pole. The objective is to move all the disks from one pole to the last pole, okay? You have one pole in the middle that you can use for kind of like a temporary storage thing. The rule is you can only move one disk at a time. So you cannot just pick up the entire stack of disks and go like drop and go like, I'm done here. You can only move one at a time. That's the first rule. The second rule is you cannot have a bigger disk sitting on top of a smaller disk. So there are these basic rules. And as it turns out, it makes the problem kind of difficult because the solution, the number of steps to solve it, is proportional to 2 to the power of the number of disks. Okay? And that's kind of the nature of the problem. Okay? So the Tower of Hanoi has also a lot of kind of background stories. I think one of them has to do with a temple. So these monks are trying to solve this problem involving 64 disks. And the idea is when this problem is solved, it would also be the end of the world. You can look at Wikipedia. I'm not making this up, okay? I am not making this up. So the idea is when you can solve the Tower of Hanoi problem involving 64 disks, then it would be the end of time, the end of existence. And then somebody actually calculated 2 to the power of 64 and then make certain assumptions of physically how long it takes to move one disk from one pole to another pole. And as it turns out, 2 to the power of 64 times that amount of time is an insanely long amount of time anyway. So we got nothing to worry about. We got some other stuff to worry about way before this one is done. Okay, so that's the Tower of Hanoi. So the Tower of Hanoi problem is interesting because it can also be done recursively, and this is the recursive version of how to solve the Tower of Hanoi problem. So you are, okay, so as an invocation, you are given n disks. You're given the index of the from pole, you're given the index of the to pole, and you're also given the index of the pole in the middle that you can use as quote unquote a temporary variable. And the way to solve the problem is to divide it into two main halves. The big half, the first big half, is to move n minus 1 of those disks from the from pole to the via pole using the to pole. And then you move the one disk that is remaining from the from pole to the to pole using the via pole, because the via pole is not going to be used in this case because you only got one disk. and then you move n-1 of the disks from the via pole, which is your temporary variable, to the to pole using the from pole. You can find animation. I know this looks really dry and boring, but you can find animation online that will show you exactly how the disk got moved. And it's fun to watch for the first 5 minutes, maybe 5 seconds. And then after that, you go like, okay, yeah, I got the idea. I get the idea. Okay. So a problem like that complex, can be encoded in recursion, using recursion to be something that simple. Okay. And also we have delete directory, which is usually also recursive. So nuking a folder is recursive because you cannot, in most file systems, you cannot remove a folder unless the folder itself is empty. That's a general rule of most operating systems. So that means if you want to nuke a folder and it has a subfolder, you have to go to the subfolder first and say, okay, I have to nuke the subfolder. But if the subfolder contains other subfolders, and then you have to nuke all the subfolders, so it becomes a recursive problem. Okay, this is also why in Linux, if you go to the command line, okay, let me show you here, the rm command. Now I need to get to a place where it is relatively safe if I accidentally press the enter key. So rm-r is the recursive version. Okay, it allows you to remove folders and not and also the subfolders and the subfolders and so on recursively. So there are a lot of things that we can perform in a recursive way. Some of those make sense to do it recursively, like Tower of Hanoi. Okay, it is natural to solve that problem recursively. Other things like factorial, Fibonacci, and so on, it doesn't make as much sense, okay, to try to solve those problems recursively because there are much faster algorithms that can solve those problems non-recursively. So when do you want to consider recursion? Recursive algorithm can be converted into iterative, which means using loops like for loop, while loops, and so on, and vice versa. This is illustrated by the implementation of recursive algorithm using languages that do not support recursion to begin with. In other words, in the good old days, when we only got Fortran, COBOL, and I cannot remember the third programming language that was also that cannot support recursion, but yet, if you look at Dijkstra's algorithm, it's not recursive. It can be recursive, but it's not. So there are ways to do things non-recursively to solve problems that we usually use recursion to solve. I can give you a story. This also relates to my dissertation. I have to run some simulations, like how do you solve the problem, how long is it going to take, and so on, and what kind of path do you find. So I wrote a recursive algorithm first. It was running insanely slow, okay, on my first generation ThinkPad. So that was not good. It was not good to the point where I had to rewrite the entire program that was recursive. I had to convert the recursive algorithm to something that is non-recursive. There's a very useful technique to do it. You basically have to maintain your own stack, that's all. Okay, and your own stack is just an array. Okay, you just have to maintain where's the top of your stack. You have to do the push and the pop operation accordingly. As long as you can do that through a lot of tedium, you can convert any recursive algorithm into something that is non-recursive. In the process, what you gain is efficiency. Tremendous amount of efficiency, but what you lose is readability. Your algorithm will have to break the logic into a lot of fragments, so it doesn't look like one contiguous piece of logic anymore, because you now have these tiny little fragments kind of sprinkled everywhere. But the whole point is you can do that. Okay, you can convert recursive into non-recursive, non-recursive back to recursive, so they have the same expressive power, so to speak. So recursive definitions, usually would make a good candidate to be implemented recursively. So we have seen a few in this class, right? So the algorithm to generate all the combinations is recursive. The algorithm to generate all the permutations is also recursive. So the definitions is recursive to begin with. So it kind of makes sense if you're given a recursive mathematical definition and you implement it using a recursive subroutine, that kind of makes sense, okay? Except it does not. Look at Fibonacci. So Fibonacci can be defined recursively, but to implement it recursively is unnecessarily inefficient. It just takes a lot of time, which is close to 2 to the power of n. Except you don't have to do it that way. Okay, it can actually be implemented in a log n way. Let me say that one more time because I think some of you did not catch what I said. The Fibonacci series can be computed using a log n algorithm. Most people say, yeah, we can make it big O of n. That makes sense, right? Because what you do is you solve f of n, f of 1, f of 2, and you retain all of those smaller numbers, or you just retain the second to the last. I think you won't have to retain like 2 of them to compute all the higher ones. So it'll be order big O of n, which is linear. Okay, the linear approach makes a lot of sense. But there's actually an approach of log n. I'll give you an example. Okay, to figure out f of 500. Okay, you only need log 2 of 500 iterations. Isn't that kind of interesting? You can look it up. Okay, the person who proposed this really super fast algorithm was Knuth. Does anyone know who's Ronald Knuth? Doesn't ring a bell? Okay, how many people know what is LaTeX? The language that I use to write all the equations. It's LaTeX. So LaTeX, not the LA part, but TeX, the typesetting engine, was written by Ronald Knuth. So you might ask, who's Ronald Knuth? Why does he have all this spare time to write a typesetting program? And why would he want a typesetting program to begin with? Well, because he was a professor at Stanford University. And he is one of the modern father of computer science. Can anyone guess who's the other one? Because we have talked about that name already in this class. Dijkstra. So between Knuth and Dijkstra, those two were considered the modern fathers of computer science because they wrote more algorithms than I cannot compare. But most of the known algorithms today, many of the useful ones, are written by one or the other. So you can look up those two names. I would definitely, maybe after the final exam, I would look into this, right? Knuth, Dijkstra, Dijkstra. And these two they have a lot of discussions. So Knuth has opinions on what Dijkstra has to say and vice versa. Dijkstra passed away already, several years ago, and Knuth, I think he's still alive in Palo Alto. But these two have different opinions, and one of the differing opinions that they have on has to do with whether computer science is math or not. And I think that is relevant to this class. Okay, in a very weird way, it is relevant. Dijkstra is the diehard one that basically claims computer science is a field of mathematics, period. Okay? In other words, all the classes designated as CISP really should be just math. Okay? Knuth, on the other hand, basically says, well, with modern programming languages and IDEs and so on and so forth, we don't really need people to have a super strong background in math to become, developers or programmers. So they hold slightly different opinions on this one piece. Well, since I have already squandered a lot of time today, might as well squander the rest. What do you think?
I think that I agree with Dexter that it's more like math. Like, well, you don't realize it, but over time, like, you can talk to a mathematician about like how they might fiddle with in a calculation for like days on days. But then you're like, oh, that's kind of crazy, like doing math for that long. But then you're stuck on creating a system for yourself because of some random thing you wanted to test out. So I think that they have similar tendencies, and you can grasp a lot of things with computer science that a mathematician can grasp with math, and they kind of overlay in that sense.
Mm-hmm. Okay, that's a. Yep.
I was watching some YouTube videos of software engineers, and they said after graduation they haven't been using math as much.
Okay, well, not explicitly. So they could be applying what they have learned, the techniques, without realizing that I just reapplied the technique that I learned from one of my classes. Because most people cannot trace the source of what they know all the way back to the class or the moment when they learned that concept. So I can sort of see what you're saying, that they don't feel like they're reapplying, what they have learned in college. But at the same time, once you absorb the knowledge, it becomes indistinguishable from everything else that you know. Yep.
I think you're ultimately limited in this field by how much math you know. So you go pretty far with a little amount of math, but if you really want to go to the ends of the field, you need a very strong mathematical base.
Or if you want to be that guy or that gal, that person who makes a breakthrough in something, math usually is the tool to do that. Yep.
I was gonna say, I feel like the majority of computer science now isn't really that math related, but bleeding edge stuff is, I feel like it's almost all math required. Like if you're working at NVIDIA, trying to crunch out chips.
Mm-hmm.
I mean, like even the progress they make, like even the smallest optimizations make a big difference in data center settings.
Right. So I'm just doing this search here, which is kind of like why would you do something like that? There we go.
To say 4 billion.
25 billion eigenvalue, the linear algebra behind Google. I think the math professors should know this. They can get more people to take math classes or pay more attention in class. Yeah, I mean the whole search engine thing, or at least the original Google search engine, was a mathematical concept based on eigenvalues. Now I'm really kind of regretting that I did not take enough math classes. So I took linear algebra, but they never really not the advanced version where they talked about eigenvalues. So eigenvalues, I could look it up. I could look at Wikipedia to learn what it is, but I would not be able to apply that. One of the founders of Google recognized that Google search, or what we now term as Google search or internet search, can be solved using eigenvalues, and that was a math thing, right? I mean, if you know the math, you recognize from this problem, and you just map it to some tools that you have learned in your math classes, and go like, oh yeah, that problem can be solved with this. You're not bothering with all the string functions and all the ad hoc way of searching, matching, and stuff like that, because you're mapping it in a much more elegant way to a problem that has been solved in math already. They got the solution already. Okay, so that's one. I'll present to you another piece of evidence, which is how Knuth solved the Fibonacci problem. Not linear algebra. Yeah, actually, I take it back. It is linear algebra. It is a linear algebra. So Knuth log 2 of n Fibonacci algorithm is also based on linear algebra and a very astute observation of the Fibonacci sequence. So once again, it is math-based. And you might be asking, n versus log n, they're both good, right? I mean, it's bad when we have n squared, n cubed, 2 to the power of n, those are all bad. But what is the difference between log n and n? I mean, well, the human population on this planet just exceeded 8 billion, right? So if you are to search, okay, in an array for a specific individual, okay, let's just say the array is already sorted by whatever key that you're searching with. So it's already sorted. Linear search will still be big O of n, because on the average, you have to search half of it to find what you're looking for. Okay? Binary search, on the other hand, is log 2 of n. So you're basically looking at the average of 4 billion iterations versus how many? What is the log 2 of 8 billion? Okay, let's do this without calculators. You don't need a stinking calculator for this. Because 1,000 is approximately 2 to the power of 10. So 10 to the power of 3 is approximately 2 to the power of 10. So use that approximation. 1 billion is 1,000 cubed, right? Which is approximately 2 to the power of 10 cubed. So 2 to the power of 10, then cubed, is 2 to the power of 30. Then we have the extra 8 that we have to take care of. 8 is easy, right? 8 itself is 2 to the power of 3. So 8 billion is approximately 2 to the power of 33. Is that okay? So that means with binary search, you can locate the one item that you're looking for or confirm it's not in the array in 33 comparisons. As opposed to linear search, even with sorting and knowing that the array is already sorted, you will still be looking at billions of entries or searches, the iterations through the loop. It makes a huge difference. So once again, it's about the math, okay? If you have a really strong math background, even though you don't realize it when you are working on solving a problem, those are tools. They're in your pocket. They're in your toolbox. And most of the time, if you can map, the problem that you're trying to solve to the math concept, it can really help. And I think, this really makes a difference between someone who is a coder, a developer, or even a software engineer versus someone who is doing research and be able to find, just make that breakthrough, okay? Like Google, okay? Google is a breakthrough because, how did Google compare to Yahoo back during those times when Google first came around?
Yahoo was the big dog.
Yeah, Yahoo was the big dog, but how did Google win Yahoo in the search engine war?
It was just more efficient.
It's much more efficient. It's more
accurate.
Mm-hmm. And I will bet you that Yahoo did not use eigenvalue as a basic mechanism to perform the matches between the entries. So, all right, well, we're done today. I would like you guys to kind of take a look at the Prolog program because it's kind of cool. It's kind of like a combination between searching the graph and Prolog. So I think it's kind of interesting in that sense. So I'm going to give you the source code. I'll send it to you guys. And then from here on, we'll just be focusing on the complexity of algorithms. And we'll kind of dive into the math part of this a little bit. All right, I'll see you guys on Wednesday. See you, Mike.